ये करनी है। Okay, now in today's meeting of thermodynamics, in today's meeting we are going to discuss entropy. Now, what exactly is entropy? Entropy of a system is the degree of randomness or disorderliness of the system. So that is called entropy. So the thing is that but we need a mathematical definition also. So if entropy is more, that means system is more disordered. If entropy is less, that means system is less disordered. But we need a mathematical definition also. So the mathematical definition of entropy, suppose let us say that a system is going from state 1 to state 2. Okay, suppose there is a system which is going from state 1 to state 2. So it may go from state 1 to state 2 in any way, but if it goes from state 1 to state 2 reversibly, right? If it goes from state 1 to state 2 reversibly, then the heat that is supplied to take it from state 1 to state 2, that heat divided by the temperature at which the heat is supplied, that is called the change in entropy. So this is actually very interesting. That means like enthalpy, we don't go for the absolute value of entropy. So just like enthalpy, we go for the change, entropy also, and internal energy also. Internal energy, we don't go for the absolute value, we go for the change. So similarly, in case of entropy, we go for the change. So if the system is going from state 1 to state 2, then the change in entropy is equal to heat that is supplied reversibly divided by the temperature at which the heat is supplied. So this is the definition of change in entropy. Now you are aware that at a particular temperature the internal energy is constant, so change in internal energy will be 0. So heat supplied reversibly divided by the temperature at which it is supplied. So we can write minus of reversible work done by temperature, because you know that delta U is Q plus W, and in case of temperature constant, delta U will be 0, so Q will be minus W. So minus reversible work done by temperature. So this will be 2.303 nRT by temperature into log V2 by V1. So this is 2.303 nR into log V2 by V1. So the minus reversible work done by temperature, so that is 2.303 nRT log V2 by V1 by temperature. So it's coming 2.303 nR into log V2 by V1. So this is the change in entropy. Now, as I have mentioned to you that the change in entropy is reversible heat supplied by temperature, but in most cases the process is not reversible. Okay, mostly the process is in most cases not reversible. So if I have two states, state 1, state 2, then how do I calculate the change in entropy? Suppose if the process is not reversible, but the formula is this only. So how do I calculate? So as an example, let us say that suppose you have a sum like this. Suppose n moles of an ideal gas expands from initial temperature pressure is T1 P1 and final temperature pressure is T2 P2. So suppose n moles of ideal gas expands from T1 P1 to T2 P2 and you want to find the change in entropy. So So number one, the pressure changes from P1 to P2 at constant temperature. Okay, the pressure changes from P1 to P2 at constant temperature. So in that case, since temperature is constant, we can write 2.303 nR log V2 by V1, and we can also write 2.303 nR log P1 by P2. So since the temperature is constant and pressure is changing from P1 to P2, so we can say change in entropy by using that formula which I showed you. 2.303 nR log V2 by V1 or 2.303 nR log P1 by P2. Secondly, temperature changes from T1 to T2 at constant pressure. So first the pressure changes from P1 to P2 at constant temperature, then the temperature changes from T1 to T2 at constant pressure. So for this, the change in entropy will be you know that constant pressure we can use N into Cp. Cp is a molar specific heat at constant temperature. Integral dt by T from T1 to T2. So this is coming to 2.303 Ncp log T2 by T1. So this is delta S2. So this is delta S1 and this is delta S2. So delta S total will be .303 nR log P1 by P2 plus 2.303 Ncp log T1 by T2. So that means if you have a question given to you where the system is going from state 1 to state 2 but not going reversibly, then you can proceed like this. You can break the passage of the system from state 1 to state 2 into two parts and proceed like this. So in this way you can do it. Now, just like you have isobaric means constant pressure, isochoric means constant volume, isothermal means constant temperature. Similarly, you have something called isentropic. So isentropic means entropy is constant. So entropy is constant means change in entropy will be zero. So this entire thing you have to equate it to zero. So Cp log T2 by T1 is R log P2 by P1. So for this process, if it is isentropic, the change in entropy will be zero. You will get this equation. Okay, now we come to the second law of thermodynamics. What does the second law of thermodynamics say? Suppose a system is going from state 1 to state 2 reversibly. So change in entropy of the system is reversible heat supplied by temperature. Change in entropy of the surrounding is minus of reversible heat supplied by temperature. So total entropy change is this plus this, that is equal to 0. In case of irreversible process, change in entropy of the system will be the same only, because that is a definition, reversible heat supplied by temperature. But change in entropy of the surrounding will be not minus QREV by temperature, it will be minus Q irreversible by temperature. Because the process is irreversible, so for surrounding it will not be minus QREV, it will be this. Now the total of these two will be positive. So according to second law of thermodynamics, if the process is reversible, the entropy change is 0. If it is irreversible, the entropy change is positive. But under no circumstances, the entropy change can be negative. That is called second law of thermodynamics. That means the total entropy change for system and surroundings will always be positive unless it is 0. That is called second law of thermodynamics. Now, since the definition of entropy change is that it is heat supplied, reversible heat supplied by temperature, so if the process is adiabatic, then change in entropy will be 0. Okay, for adiabatic process, entropy change will be 0. Suppose if you have a reaction like this, 2NO2 equal to N2O4. So here 2NO2 and N2O4 from the point of view of stoichiometry, they are looking the same. But N2O4 is a bigger molecule. So a bigger molecule will have more entropy. So 2NO2 equal to N2O4, that means N2O4 will have more entropy since it is a bigger molecule. Another example of bigger having more entropy, another example, actually the thing is that in aluminium oxide, the cation is Al3 plus. Now if Cr3 plus replaces Al3 plus, suppose in aluminium oxide, Cr3 plus replaces Al3 plus, in that case Cr3 plus is bigger and Al3 plus is smaller, so ruby will be formed. So whenever a bigger one replaces a smaller one, ruby will be formed and the change in entropy is positive, right? So Cr3 plus replaces Al3 plus to give ruby, but during the process entropy change is positive because this is a bigger cation than this, so the entropy change is positive. So these are all examples that bigger species will have more entropy. Okay, now next actually, suppose if you have a sample of gas and the pressure is low. So when the pressure is low, then the gaseous molecules, they tend to move around more randomly. But suppose if the pressure is high, high pressure means low volume, the gaseous molecules have less randomness. So lower pressure, so at lower pressure, okay, so basically if the pressure is low, then they will have lower entropy, and when the pressure is high, due to high pressure, the molecules will be more agitated and therefore the entropy will be more. So this is another important thing. Okay, now suppose there are two bulbs in which there are two gases. Suppose this is a bulb A, this is a bulb B. So in the two bulbs there are two gases, and you now allow these two gases to interact with each other. So the change in entropy of A, so we had seen one formula earlier, that is log P1 by P2. So the change in entropy of A will be 2.303 nR log PA by P total. You have allowed the two gases to interact. Initially there was a valve, you have opened the valve and they are interacting. And the change in entropy of B is 2.303 nR log PB by P total. Okay, now the most efficient heat engine is Carnot's engine. So it is a reversible engine. So So the efficiency of Carnot engine is work output by work input into 100. Efficiency of any engine is work output by work input into 100. And in case of Carnot's engine, if you take the system from temperature, like basically the process is happening between two temperature. One is a hot reservoir is T2 and the other is a cold reservoir T1. So the efficiency will be 1 minus T1 by T2. So there is another way of calculating the efficiency of a Carnot engine. You can write 1 minus T1 by T2. You can say that if X% of the work done is dissipated as friction or heat or something, so you can also write 1 minus X% of W divided by Q. So it will be 100 minus X by 100 into W by Q. So this is the efficiency of the Carnot engine. So suppose you have two bulbs. I am now giving the homework question. Suppose you have two bulbs, bulb A and bulb B. 1 mole of nitrogen, 1 mole of nitrogen. 298 Kelvin 4 bar, 298 Kelvin 2 bar. So you allow the two to mix isothermally. So the question is, what is the final pressure? So options are 6 bar, 4 bar, 2 bar and 2.67 bar. So these are the two bulbs. You allow them to mix together and isothermally. So what is the final pressure? Options are 6, 4, 2 and 2.67. Secondly, what is the entropy change? So options are 0.96 joule per Kelvin, 3.35 joules per Kelvin, minus 2.4 joules per Kelvin, and minus 0.96 joule per Kelvin. So during this entire process, what is the final pressure and what is the entropy change? This is the question number 1. So suppose there is a ideal gas, it is going from X to Y to Z, the pressure and volume is given. So it can go like X to Y to Z or it can go directly, anything can happen. So the change in entropy, if it goes from X to Z, is equal to change in entropy X to Y plus change in entropy Y to Z, that is option A. Option B, work done X to Z is work done X to Y plus work done Y to Z, that is option B. Option C, work done X to Y to Z is work done X to Y. Option D, change in entropy X to Y to Z is change in entropy X to Y. This is question number 2. You have to select all the correct options. This question is from JEE Advanced 2012. Question number 3. So there is 5 moles of argon at 298 Kelvin at 10 atmosphere. It is isothermally taken to state Y, which is at 1 atmosphere. and adiabatically taken to state Z. And this is isobaric. So the options are change in entropy from X to Y is 95.7 joule per Kelvin. Change in entropy from X to Z is 0. Change in entropy X to Y is entropy change X to Z plus Z to Y. That is 95.75 joule per Kelvin. And option D, change in entropy X to Y to Z is 0. So once again, the options are change in entropy X to Y is 95.7 joule per Kelvin. Change in entropy X to Z is 0. Change in entropy X to Y is X to Z plus Z to Y. That is 95.75 joule per Kelvin, and X to Y to Z is 0. Okay, and the last homework question for today is that a system is going from state 1 to state 2, and a system is going from temperature T2 to, like a system is undergoing Carnot reversible cycle between temperature T2 and T1. So if T2 is 298 and T1 is 273, that is condition 1. If T2 is 298, T1 is 240, that is condition 2. So the question is find the efficiency of 2 divided by the efficiency of 1. That is the question. So T2 298, T1 273, that is 1. T2 298, T1 240, that is 2. So find efficiency of 2 by efficiency of 1. So that completes all the 4 homework questions of this particular session. That also brings us to an end of this session. The next session will be on Monday, and today's homework you will have to submit by 9 p.m. of Monday, right? So that's it for this session. I'll conclude now. Thank you. Bye all of you.